Hey guys, today we're going to be looking at the introduction of stoichiometry. Stoichiometry is essentially the math of chemical formulas in the form of a chemical equation. And today we're going to be looking at the most foundational part of that, which is what we call the mole ratio. This is going to tell us the relationship between the reactants and the products in chemical equations. So before you guys actually watch this video, make sure that you're confident in not just what is the mole, but also how to balance chemical equations and how to utilize unit conversion and dimensional analysis techniques to solve problems. Let's start by looking at a chemical equation. Now, in a chemical equation, we've already talked about how we use subscripts in chemical formulas to tell us how many atoms of each element are within a compound. And we also talked about how we can utilize coefficients to balance chemical equations from left to right across reactants and products. But today what we're going to do is we're actually going to analyze these coefficients, because the coefficients are what are going to lead us into what we call the mole ratio. For instance, in this chemical equation, we're dealing with the synthesis of water, H2 plus O2 react to yield H2O. Now we know that in order to do this, we need 2 in front of the H2 and a 2 in front of the H2O for the equation to be balanced. But what does this actually mean? The 2's tell us that if we're looking at these reactants or products as ingredients or products of a chemical reaction, we need 2 molecules of hydrogen plus 1 molecule of oxygen, which lead us to produce 2 molecules of water. Remember, we can upscale from molecules to moles simply using Avogadro's number, 6.02 times 10 to the 23rd particles per mole, which means that not just 2 molecules of hydrogen plus 1 molecule of oxygen, but 2 moles of hydrogen plus 1 mole of oxygen. The mole ratio is essentially the same thing as our molecule ratio. So what we can do is analyze the relationship between hydrogen and oxygen here to make predictions on how much we would need for a chemical reaction to occur, and also in terms of how much product we can produce. Let's relate this back to our cooking analogy. Now, in our recipe, if we needed 2 cups of flour for every 1 cup of water to create 2 loaves of bread, the ratio between flour and water is 2 to 1, and the ratio between flour and bread would be 2 to 2, or 1 to 1. If we were to try to double the recipe, we would have to double everything, which means we would need 4 cups of flour, 2 cups of water, and we'd be able to produce 4 loaves of bread out of that. In addition to scaling up, it can also scale down. Let's say instead of doubling the recipe, we want to halve the recipe. This means we'd cut every ingredient in half. So instead of using 2 cups of flour, we'd only use 1 cup of flour. And instead of 1 cup of water, we'd use half a cup of water. And instead of producing 2 loaves of bread, therefore, we'd only be able to produce 1 loaf of bread. So chemical equations and recipes can both be scaled up or down, but the critical factor is the ratio between ingredients or reactants and products is going to remain constant. If you want to create more products, you simply add more reactants, and we can predict this using this ratio. So let's talk about that. Let's look back at our chemical equation now. Remember, we had 2 molecules of hydrogen and 1 molecule of oxygen that led to 2 molecules of water being produced. If we were to need to double the amount of water produced, we'd simply double everything. Double the amount of hydrogen and double the amount of oxygen. We can think about this in molecules, or using our scaling factor of Avogadro's number, we can think about this in moles. In other words, if we want to double the recipe, we can have 4 molecules of hydrogen, or 4 moles of hydrogen, 2 moles of oxygen, which can produce 4 moles of water. Now let's talk about how we can use dimensional analysis to solve problems in this context. When I talk about an equivalency in dimensional analysis, this is 2 things which are equal. Now, 2 things which are equal means that we can use, say, Avogadro's number, which is particles per mole, or molar mass, which is going to be grams per mole. But in stoichiometry, we can use what's called the mole ratio. The mole ratio is going to simply be the relationship between the coefficients of each of the 2 things we're converting from and to. For instance, the ratio between the oxygen and the water is 1 mole of oxygen to 2 moles of water. So what we can do is actually put these as a fraction with units of moles of oxygen and moles of water, and that becomes an equivalency. That allows us to convert from moles of water to moles of oxygen. Let's show an example of how we're going to do this. In this first example problem, we're given that we have 3.89 moles of oxygen, and we need to find how many moles of water can be produced from a chemical reaction. In order to do this, we're going to use dimensional analysis, which means we're going to first write what we're given, 3.89 moles of oxygen. We then need to find an equivalency to convert from moles of oxygen into moles of water. Well, as we just discussed, this is our mole ratio, which is the ratio of coefficients. Now, in the balanced chemical reaction, we see that we have 2 moles of water for every 1 mole of oxygen. Therefore, the ratio we're dealing with, we need to divide by moles of oxygen to cancel out moles of oxygen and multiply by moles of water. So we're going to multiply by a ratio of 2 over 1. Don't forget units. We want to make sure our units are canceling. This means that we end up producing 7.78 moles of water from our original 3.89 moles of oxygen gas. Now let's take a look at another example. In the second example here, we're dealing with the exact same balanced chemical reaction, but now instead of finding how much product can be produced, we need to figure out how much reactant is necessary to fully react with our 3.89 moles of oxygen gas. We need to figure out how many moles of hydrogen gas would be needed. So in order to do this, we're going to do the same dimensional analysis, but we're going to convert from moles of oxygen to moles of hydrogen gas. In order to do so, we still use the mole ratio. In this case, the mole ratio is 2 moles of hydrogen gas for every 1 mole of oxygen. This means we write out the oxygen, 3.89 moles, divide by 1 mole of oxygen, and multiply by 2 moles of hydrogen gas. This means that for 3.89 moles of oxygen gas to fully react, we need 7.78 moles of hydrogen gas present. For this third problem, I want you guys to try it on your own. So take a second, go ahead and pause the video, and what I want you to do is either when you get stuck or get to the answer, I want you to unpause the video and we'll work through the problem together. Now you've had a few seconds to work on it, let's go through it. First things first, I give you the actual reactants and products, but I didn't give you the chemical equation, and I certainly didn't give it to you in a balanced form. So that's our first step. We need to first write the chemical reaction equation and then balance it. Now once we do this, we see that there's calcium hydroxide, CaOH2. Remember, the hydroxide has to be in parentheses when there's 2 of them, plus nitric acid, HNO3, react to yield calcium nitrate, again, CaNO3 in parentheses 2, and water. This is not balanced. In order to balance the chemical equation, what we need to do is have a 2 in front of the calcium nitrate and a 2 in front of the nitric acid. So this is going to fully balance it. If you need to review balancing, again, make sure you go back to that video earlier to make sure that you're confident with your ability to balance chemical equations. Now that we have our balanced chemical equation, we can actually go about answering this question. The question states that we have produced 0.000674 moles of calcium nitrate, and we need to figure out how many moles of nitric acid were necessary to produce that. In order to do this, we start by writing out the value that we're given, 0.000674 moles of calcium nitrate. Don't forget the units. We're then going to use our mole ratio between calcium nitrate and nitric acid to solve this problem. Now, the ratio here between our balanced chemical equations coefficients is going to be 2 moles of nitric acid to every 1 mole of calcium nitrate. This means we're effectively multiplying by a ratio of 2 over 1. This leads us to an answer of 0.00135 moles of nitric acid necessary to fully produce 0.000674 moles of our calcium nitrate. So that wraps up today's video. Let's quickly recap. We started today by talking about how the mole ratio in a chemical equation is very similar to the ratio between ingredients in a recipe. We can use dimensional analysis to solve for the amount of products or reactants as it relates to a given amount of product or reactant, and we did so in a couple of example problems, and then you guys tried one on your own. I hope you guys enjoyed today's video. I'd like to thank Kira Hobson for writing, filming, and editing it. I'll see you guys in the next one.